Good evening. Or whatever it is, wherever you are. So I did a little bit of data editing, just kind of rough in some lines, and there's a lot of crazy lines. We're kind of exposing lots of design issues. I did try bringing up the size on Artemis. I think maybe I brought down Athena since then too. I think I actually found out some other issue with the Athena layout. This is one where I'm going to try rotating it back so this thing is up down, and they can kind of take the low road and there's a high road somewhere, I think. Or maybe it's just that. But there was something else that was surprising. Oh, this thing there, and I hadn't. And I think I actually have to just go back and reconsider flare entirely. Artemis. Oh, actually, no. Artemis is where I had a lot of flare surprises when I started hooking things up. Because that counts for more stuff than I expected, but not necessarily for everything. So that continues to be a mess. We know we needed to move Zeus for a while. I think these are off of the aid, but these are actually off any aid. So that might give us a little bit of design freedom on those. Anyway. Oh, and we have a bug with Ares, which I guess I need to put this into regulation position to see if it has to do with rotation or what. So that is not being properly updated. But the big thing is to get these wonky lines fixed. Oh, and I edited a bunch of stuff. SVG elliptical arc API one needs to convert from endpoint parameterization to center parameterization. Well, all right, so we don't necessarily have that. We're trying to kind of keep things in an abstract format. Might have to do a few conversions. All right, so they have a few, and I guess we're probably going to want these, and then we'll have to decide if we want to end up putting these in geometry or what, because this is like an ellipse parametric equation. That is a geometric thing. I don't know how useful it is. Wait. It gets cosangle and sine angle, not just angle? But then they do like acos this thing, so why is that an input? Okay, yeah. Oh, these are variable names that are those pre-computed values. Okay. So I guess that's just because we used it twice. They were doing this. For simplicity, I might just do that as an angle. We can revisit the performance part of it later. So you have a center. Wait, what's R? RX, RY. Okay, so this is... Interestingly enough, if you talk about the major and minor axes, you do... It's kind of a vector? That's not how I've been representing it. So I actually have a type that represents an ellipse in the other module. And that has all that stuff broken out. Wait a minute. Oh, no, that's A times, not ACOs. Actually, I guess we're even using them twice in here, and it's passed to the methods twice, which is why he broke it out. Elliptic archetype. Center, major, minor, and this is the angles. This point is only at a single angle, so this is elliptic arc. It's not... The point, this is a point at a single point. So I could do center, major, minor as the ellipse. Oh, you know what? Even this is not semi-major, semi-minor axis. This is major axis, minor ratio, because that's how we received it. Wait. Was I just thinking about changing that between these two? I thought I actually did change it. Or maybe I put that off till later. Yeah, and then we calculate this stuff. I just have these in the context of this. What was I using you? I'm not anymore. Okay. Okay, so all you need Wait, is this the angle of the ellipse? Or the angle we're at? For n times. Okay, this is the angle of the ellipse. Wait. No, does that just turn back into my major axis? I don't have a good place to output major axis. If so, that's kind of interesting because that actually means that major axis form is actually a useful intermediate format. Because this actually printed out less, and no, it is not the same. Oh, although this is not scaled by length. Well, this is still cosine of angle, not... Although if we normalized it... Yep, that's exactly that. Does that mean we don't need the angle? This is given angle. Huh. Is that right? Sine is that one. So we need the center. We need cosine sine. We need the angle we're at. We need... Oh, we also need the semi-major and semi-minor. That's not quite like rescaling a vector. Well, it's a non-uniform scaling, which makes sense because we're an ellipse. And the A and B in this one are different, although that would kind of just wash out to some minuses on the A there. Because otherwise, this is actually, that derivative thing is very similar. What would we call, oh, are those flipping, no, Rx cos, Ry sine. What do we call you? You're just a factor in one equation. Maybe we keep that in the function for now, but that it could be a candidate for extraction. Oh no, because that involves t. That is not these things. All right, so center is known. Semi-major and semi-minor are known. Cos A and sine what? They are known. So this is really only a function of an angle. And this is just plus center. Let A equals, our x is the semi-major. No, not, yeah, whatever angle we're given. And then the rest of that is A times cos angle minus B times sine angle, A times sine angle minus B times cos angle no grave sins yet. Oh, we did angle twice. Yep, there's that angle. All right, we can't call it A if we're using A and B there. I guess we go with T. All right, and then our tangent Exact same parameters, but it's a dx, dy. So I'm not going to add center. Wait, why does it take center as a parameter? I guess it was just to keep the signatures similar? Since we are calculating these separately. Fuzzy moment. All right, A times cos angle minus B times sine angle. A times sine angle plus B times cos angle. Oh wait, does this change sign? Determine the angle between two vectors, which we already do. And this probably ends up being similar. So you're doing a step angle. So we're forming a vector. Oh. I did a length operation, so that's going to implicitly do the absolute value. Center parameterization from this parameterization. Well, I actually think this angle start and angle end, if that's what that is, might actually be closer to what we want. Well, these are two angle deltas, so I'm not sure what that is. That's how many segments you're going to do. We can keep on working with midpoint for now. It's been manageable so far. So we have that from there. So he's setting up to do a step process. We have a starting point, a starting tangent, this is an angle step. We have a t, at t. Oh, at start angle plus this. So this is the, wait, P2. Oh, he's using P1 and P2 as the endpoints and Q1 and Q2 as those points. So he's calculating the point and the tangent. At the t. Oh, and this is the pre-computed. Right. So there was a function that we had for circles. And maybe this actually fills more of this role, because this gives us our cubic. Given point, and the center. And we were just calling out to this. Right, because we had a form that could just take this and then arc from angles. Okay, cubic curve is our drawing operation. Right, because our duo arcs are in point form, so they take that point form. Curve points from angles is using this kind of internally. But really, as long as it returns the points, we're okay. It's just this was a bunch of math. Which, do we want to be able to extract that? Okay, this is where we might want to extract it when we're doing the two sections. Right, so we were getting these points, but then we were using that curve. But the elliptic curve points would need a bunch of parameters, it looks like, to be able to... A couple of these are going to be larger. Actually, most of the ones that look really awkward are probably going to be larger. Which means it's actually going to be this. So we calculated points because that was a points to form. And then we've got the, okay, so actually a bunch of this was calculating that A factor. Which he did the step with the constant. And then this part looks essentially the same. But this part uses this stuff, which is currently relying on derivative parameters. Well, how much are you relying on? Semi-major, semi-minor. Cosine, which is major axis. Oh, and center. Which we skipped passing to that because we were just in this context here. So an endpoint and a tangent. The tangents are used in calculating our Q points. And it's not exactly the same because it's plus and minus. All right. Do we actually want to calculate the points now? No, the cubic is still the points. Wait. Times angle. Oh, so this is actually... So that's the same as this. Right, yeah, so if we have a shared point, that'll be the same. The tangent at the midpoint will also be the same. So this is just a different way, and this is basically rotation. By ellipse angle, and is this basically rotation by that angle? Well, but we're doing the ellipse scaling on that. So midpoint NA and NB could equivalently be replaced by this ellipse point of the angle. And actually that would continue to work in the existing code, which is still watching the angles because of circles. Oh no, that is objectively worse. I wonder if, like, our angle of rotation is different or something? Or our direction of rotation? Or our origin of rotation? It seems to be varying specifically in Y. I wonder if my coordinate system is just flipped. It's not by a sign there, but we are adding center to this. Okay, Rx I think is going to be the semi-major cosine semi-minor sine t. Adding center should be trivial. A times cos minus b times sine. A times sine minus b times cos. Huh. Well, there's direction of rotation. Which makes me wonder if my rotate method is the one that's backwards. No, actually there's a little bit more squiggle than there used to be. It's not the same for all of them. What? Oh, okay. It's deeper than that. That changed our x coordinate. Yeah, so this probably is like y inversion. I'm not quite sure where to do that. Maybe it is... Let me see, this is a minus. Eight, 9, 2, 1. Oh, no, we have a difference here. So it's not that. Okay, we haven't used a tangent yet, but we can probably assume we'd have to do a similar thing there. I guess that would roughly equivalent to swapping the signs on these. Or is that changing? Oh, no, that's changing the factor. Okay. So that was B, so it must be this. Okay, that is no worse. That is no worse. That is no worse. All right, so what this did is it took those points, well, it needs all the factors to do the tangents. I guess if we treated these as closures, you could pass it to the function. But maybe we have to do an internal function. So it's always going to be center. Oh, actually. This is probably all you need for center on that, huh? because it's calculating point. Okay. So this is going to need to do the gap between between the two angles, which we have our total angle here. From angle, that is... so both of these are going to be odd angles. So if we do this, then it's all one value. If we do this, then it's one other value. Let's get to the other thing. It's kind of arbitrary. We want this to be a function because well, essentially what we do depends on this. So we have a thing called step. We have a thing called t, which seems to be in radians. We've got delta angle. One thing I'm having trouble tracking is what's the difference between t and... Wait, so t here... Oh, this is finishing out, so this is the final angle. It is going to be the t minus pi divided by 4. This is backing out the last step here. So this is the... So step is the from point. T is the to point. The to angle, which is just going to be our parameters here. Maybe we can share something later. We need to... So we have two angles, which maybe for simplicity we can call step and t, just to make the translation easier and then rename them later. Oh, right. This is, well, yeah, that works. But this is actually going to look more like sin step times It actually looks kind of similar to the K2 and curve points. There's a 4 and a 3. Well, that's a 3a squared. That's a 2 times q1 times 2. Yeah, there's some other things going on there. All right, so that's the step. Oh, we've already calculated the... Well, I guess if I just took these as angles, then the points are easy to calculate, right? So in theory, we already calculated as ellipse point of step. And E1 as tangent of step. And we would be able to share some of these calculations if we were to figure out how to extract them properly. Because all the stuff for midpoint is going to be the same. And then the Q points. I guess there's a little bit of calculation here. Is P1. Well, that is a scale. I could almost skip the tangent part here. The P1, P2 is going to be an add or a sub, and that's going to kind of matter in how we do our geometry operations. Actually, I can just... I think I can just invert the A term. And that'll get us the right effect. Ellipse points from... Well, this was... Ellipse points from start angle to mid angle. Maybe I should keep these around for a little bit. And that is objectively wrong. I wonder if this has something to do with this whole sine inversion thing. I might need to try and plot tangents. Nope, that's pretty bad too. Do I have any way... I gotta check on this. Okay, we have reason to believe that our points are still being done right. And then the other thing I was doing is curve points from elliptic angles, put this into cubic curve. What was this, a path? Yeah, that's all over the place. It's so all over the place, it's hard for me to track what's going on. I don't know of a good way to strip this down to just a single one so I can kind of get a better sense of what it's doing. I think with the arcs, we had some singular arcs that were a little bit easier to pick out. Model.active basic groups. Basic connectors. The duos really shouldn't be going through. It's not too big a deal. Display boon connector. Actually, we can just do this. And then list dot take one. What did we do here? Set group a die, connector, shape, link group. Oh, is this not yet translated to our style of connector? Cons. It just should be basic connectors. Oh, list. Oh, I did you in God groups. Hmm. Well, no, it doesn't work so nicely like that. Okay, that gives us 1. It must be split because it's going all over the place. And what can we do? Okay, so our old version, control point wise, was going like that. So that's roughly the shape that that segment is supposed to be doing. Instead, it is all whacked out. The tangents here almost look like, well, this one looks like it's perpendicular. That one I'm not so sure about. Maybe if we broke it halfway through and it wasn't quite even. So what were we doing before here? Because we said that this one had its sign backwards. We thought this one might have its sign backwards. It has no effect on you, but it does put that back into something like more like a perpendicular. It's also way too large. So our other factor is like what, 0.2 or something? Or 0.2? 1.99 sounds too big. So we're saying that this is, well, I don't know which is start and which is end, actually. Oh, this was supposed to be from point to mid. This would be the mid, so this would be the start. And would it help to put you in regimented position? In terms of angles, probably. Okay, doesn't seem to have changed that at all. All right, so 3.1-ish, okay. Sounds about right. To 4.7, that's 6. That's believable. So for a quarter turn, which this is a quarter turn, so this formula is wrong because we're doing essentially, well, he's pi divided by 4. Still, that would only be, what, 0.5-ish? We're like 4 times as large. Now, we called this step, but it looked to me like it was the old angle. I wonder if this is a mistake. Like it was backing up T. But step sounds like it's the sweep. And we did some subtraction earlier. This is actually something where we could potentially pass in a parameter because we already kind of got these. And we've done some bounds checking stuff on them. Okay, so now step is 1.5. It was 3. A is 1.4. So our direction is still wrong. The size of the deflection still feels pretty wrong. So once again, we expect like maybe a 0.5. Oh, that's in the wrong place. That might be allowable as a scale of things. Now our direction is just wrong. This feels like it's an error in both. You see, this is completely unaffected. I wonder if maybe cosine sine of t are 0 at around that point. Actually, they should be opposite at most angles, shouldn't they? -3.1395, -0, 4.701. Oh. Do I have to take this entire thing and rotate it? Well, this particular ellipse is more or less axis-aligned. But I'm actually not sure where the angle of rotation... No, it's in cos A and sin A. So I think cos an A of t should give you the ordinary circular angle to something. You'd expect the tangent to be kind of opposite of that. Well, we inverted our cos. We didn't invert our terms. Does this jive with other... Actually, didn't Wikipedia have tangent? It might not be in a useful form, though. Vector parametric equation. The tangent at a point. You see, this is like an optimized version. Like, calculates the point as it's also doing the tangent. I don't really explain the terms either, so is S slope? Is S the circular angle around? Is that used anywhere else in this that it actually explains it? Standard equation. You have no S's, you have no S's. You have no S's. Only at tangent. SUV. Oh, so this is just a length of the line of any line G containing xy. Xy plus a direction vector. So were A and B like the major and minor axis or something? To the ellipse equation and respecting x1 plus su, so that's x squared. You see, this doesn't have any sine or cos in it. Of course, these are equations. They're not necessarily... Is a tangent vector at point xy. Negative y1, x1, whatever a and b are, is a tangent vector at point x1, y1. So this is a tangent vector, meaning we don't care how big it is, it just has the right direction. So we do see this sort of inversion thing, and what they're doing is negative y times a, which, let's see, what is that? What would that mean? That would mean, well, this is only the scaling factor, so this is the squish and squash of the ellipse. That's not really going to flip things. What would flip the coordinates? Would we... so actually that doesn't necessarily help. So this is a times cos a plus b times, no, a times sin a, which just seems like it's getting way, way different. A times cos a b times sin a I guess you don't like that. Oh, We lost a character here somewhere. That's closer, but exactly sign opposite. And then this looks like we still have a problem. Okay, well, we've got an A of 0.8, which is better. But still larger than we expect. Right now we're defining mid-angle by that plus that. So that is approximately pi divided by 2. He was working with pi divided by 4 and got 0.2. Yeah, we're still like almost exactly twice as big. And this is not, well, maybe if those backed up, they'd kind of work. But what we've proven so far is we cannot trust this formula. Because this is more or less the ellipse formula, not the tangent formula. I mean, if I could find this form and the reference for this form. Unfortunately, Wikipedia is not it. The normal to an ellipse at point P intersects the ellipse at another point Q. The normal. Okay, so that's kind of the normal. The angle corresponding to Q can be found by solving. The angle corresponding to Q. And then use that to get the right angle. But how do we get Q? Oh, maybe the perpendicular to the ellipse is easier to calculate? The normal to an ellipse at point P intersects. That's just intersection in general. A cos t, B sin t. What's A and B? And QT is T prime? Plus minus, I guess, because it can go either way. Does this look at anything like what we've got? There's a square root. Does not require a calculus, but it's unknown if calculus was used in the solution by the original authors. No, this is just ellipse tangent. What's T? Is that the angle Q is at? Where T is the angle P is at? Plugging this in to obtain Q, is that to calculate the perpendicular? This is from a focus form. Slope form, point form. And here's this a squared b squared stuff. Parametric form? Equation of the tangent at any point to an ellipse? Now, why are you saying A cos angle, B cos angle? What does that represent? X divided by A cos, parametric form of tangent to an ellipse. At any point. But that feels like it's a circle point, because it's just cos and sin. Oh, are A and B the semi-major and semi-minor? They're not really defining their terms here. But that would, if it was a axis aligned, that would kind of scale the factors. The equation of the tangent. We have the semi-major, we have the semi-minor. We can get the cos and sin of the angle. Just x divided by A, y divided by B. Wait, but this is just plus. What is that? That would calculate a number. Is this, even if that was if it was a singular slope number, maybe. At xy, once again, the slope of the normal we don't have any cos and y here. The equation of the normal, equation of the tangent line to the ellipse. There's some cos and y, cos and sine stuff. So here's this again. So I guess that has to be semi-major and semi-minor. M be the slope of the tangent. So this is a single integer slope factor. Well, I guess no, it's floating point, but real. equals b squared equals b squared a cos equals b cos? Right, because it's all just multiplied. There's a b and a b and an a and an a. But that's the slope. I need to translate a slope back into something. Well, here's this. Oh, here's this equals 1, which I basically need this in a vector form. So I have that, I have that, I have that, I have that. I need the x and the y. The slope of the normal. So how do we get from slope to the equation of the normal? Ax secant by cos. There's an e in there somewhere. Oh, cosecant. Equals a squared minus b squared. So I guess I need to know how to translate a slope to a vector. Nah, I think this is like a field as a mathematical concept. Well, slope is like what? Y equals mx plus b. We only need this to be a vector. That's the slope. Right, if we're at origin, I guess we don't care about the plus b. So if we calculate a slope, we just, well, times what? Do we just pick one and then say then slope is the y? And if that's like 1 to m, is that like x and y? The slope of the normal, the equation of the normal. Well, there's your slope. Now that's sort of like a y equals mx plus b-ish. But there's this y minus b and x minus a. At the point P. So what does P represent? It's just saying it's a point? Y minus, x minus. We convert, we convert, we convert. Why can we drop the x and the y out in the final equation? Oh no, that's an equation. AX secant, well, we got secant and cosecant. But once again, it's just equal. I guess you would take that and solve for y in terms of x, and then just pick an arbitrary x. You don't cite your sources, do you? I'm using the angle for the arc to the center of the ellipse. Using polylines, countermeasure curves. Curvature. Okay, so notations. This is a rotated ellipse. Ellipse E. Defined by its center, its semi-major axis, A, semi-minor axis, B, orientation, angle. Arc is defined by its start and end angles. For A and B, the circle and the direction is irrelevant. Okay, so he's talking about focus of the ellipse, which we've never had to deal with. The distance between these points in the center is blah. The coordinates of these points are... Okay, so now we have a way to calculate them if we wanted to. Parametric equations. Explicit vectoral function of one parameter giving the two coordinates x and y of the point. An angle. I need more water though. And it's probably about time to kill the webcam too. Be back in a little bit. So it's getting closer. I guess I could do a double on that one. That would change that. But then I can't do anything with this one. Because anything I do there will double up that. Okay, he is actually using turn. I wonder if he gets full turn. Or if it's going to be a little bit shorter, like, to match me. Or maybe he just didn't touch this fight at all. Or maybe it's just broken. Because his AI was written expecting a longer turn than he has. Alright, we're back. Okay, what's R? R is mathematical mystery meat. The angle is arctan 2, which was the thing that we've used to get angles. From the sine of how is this, we find a different cosine such that there's a radius that is the same. Maybe the idea is oh, here's something sort of like, pick some arbitrary circle, you can still have angles within a circle. So would this be, well, this is a point, right? At this angle. So it would be a circle intersecting that point with the equivalent angles. Or actually, no, maybe with a slightly different angle. So if we have an ellipse, I don't know if I have a good way to mark a point. Then there is some circle. Well, okay, so this ends up being a perfectly north point, so it's a bad example. I guess that'd be the same angle, actually. But there is some circle with some radius that is not either A or B, for which that would be the same angle. So I'm not sure why he uses a different notation there. He does define both of these angles in terms of other things, though, which suggests that they are different. But you kind of have to have, they're defined in terms of each other. So I guess you would get this thing from that of this angle. and then you could back that out into an R. The geometrical angle considered between one end of the semi-major axis and the current point. The geometrical angle considered between one end of the semi-major axis. Okay, so that's something different. The geometrical angle, it has, of one parameter. We use the parameter, the n angle computed. Oh, say, so there's actually how to get this angle, which is some arbitrary, I don't know. But he's indeed using lambdas here. Considered between one end of the semi-major axis. Well, the semi-major axis is here. So that, I'm assuming it's the center end? On the other hand, you'd think an end of the axis might be out here, in which case it would be this angle, which could be a little weird. Between one end of the semi-major axis and the current point, counted from the center of the ellipse. Oh, C. Okay, no, that's exactly what I would expect the angle to be. So I don't know what this thing is. But we use it in all our... Does that mean we have to do that conversion? But this looks an awful lot like the formulas we were using. Wait, the ellipse parametric equation. But now what's this? Because this is an ellipse of n. This is cos of what? Oh, the angle of the angle of the ellipse itself. Huh, a little bit of differentiation there. Which is probably showing up in, we have cos t and cos a as the angle of that. Yeah, center plus, there's the semi-major. These are all multiplied. No. Are these multiplied? Yeah, this A and B is two multiplied things. So this is kind of like an optimization in here. And then we actually have a second derivative. But okay. So there's something different about this. We have to like flip the sign or something. This is what this paper says is the tangent. And I think I'm going to have to rewrite these in the same format to be able to make it comparable. It'll be a de-optimization, but I'm going to have a lot of trouble following otherwise. Okay, those are going to get straight up inlined. Which I guess they do get inlined a few times. So I called these cos A because it was just of angle. So the equation of the ellipse at point blah 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 major axis is going to give us the angle of the ellipse. So cosine of theta is what they're using for that. Ellipse angle would then be theta, but we're not too concerned with that right now. And we have blah, 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 which probably if I looked up Greek letters. It's one of those. Eta. Time for lighting adjustments. Now you see I did t here because it was theta. But now I almost want to leave that t as oop. Oop. Not syntactically correct. Okay. So I get an equivalent form here. We have to inline this. Would it be worth... Ooh. Just to avoid some extra parentheses? Actually, this is a modification of that. Now, no, because I'm still using A and B down here. Now these, well, there was a sign difference here. I might just leave that out at this point. Actually, and this was this. Because the entire premise is that this equation is messed up. All right, now we have... Oh, I guess I could have even done this locally. I still need to free those up locally. All right. So the two angles are flipped here because of the way he pulled out the terms. But cos minus sin sin theta times cos eta cos theta times cos theta? That last one should be cosine? Right. Sin cos cos. This could have actually been a transcription error in lining stuff here. So cosine, I would expect this to be sin cos. Right, because this used to be B, and B was sin. And you were just a copy of this because the other one wasn't working. All right, sin eta times cos theta. And you are, in fact, a positive. Huh. And the first derivative does indeed involve some negatives. So this says, maybe it's supposed to be negative on both of them. Negative A, oh, because it was negative, but, well, we had all kinds of problems with this. A times derivative. It is not cos. It is cos theta times... Oh, no, wait, but this was the formula that we reported here. Oh, which we don't have... A was a cos? Yeah, but that would be wrong. A would be cos eta? And the eta factor switches to a sin here, which says that this is probably a transcription error. This should have been sin. All right. All right, so sin, this should be sin eta times cos theta minus, and the signs here seem to be the same as we're using, at least based on the point up there. B times sin theta and cos eta. Theta and eta, wonderful. And you know what? Actually, this would actually be even easier to compare here. Well, I'd have to switch my theta and eta to make it really easy to compare. And then sin eta times sin theta plus b times cos eta times cos theta. So given the really flipped tangents we were having, that seems a little bit more believable. Right, and we had cut down our angle to make it easier. Oh, because we were worried about this A factor, which is still off. Compared to our, so the tangent, yeah, because that's still saying the A factor is too big, but I'm liking these lines better. So we have this stuff. Oh, did I put the -1 in the wrong spot. No, this is all the square root. That was just extra stuff. Square root of that term -1 all divided by 3. So that might actually explain that. Hey, 0.26. That looks a bit more believable. That looks kind of believable. So where did we put That looks like kind of a nice little curve. Okay. We're gonna probably want to get rid of the spam before we turn everything on. I guess there's not that many. And we could potentially go back and re-optimize some things. Right. Take one. Quick check on this. Well, that's looking much better. All right, and then we had, oh, and there's a question of rotation. Oh, this is boon charge, just a different spot. Initial. That's all holding up nicely. I guess we have to consider this a separate thing. I think I want to checkpoint that before I go trying to optimize things. So we could pull that out into more external functions, although we would not be able to use the closure as much. So we'd have to pass in a bunch of parameters and derive some things and figure out what that means. Right. Where's the webcam still on? Must be something new in OBS. Maybe I'll ask around about that. Because I think before, if I turned off the camera, it would actually shut it down. Yeah, so this was a slight optimization. What would our parameters be if we wanted to pick these full functions? We'd have the angle, we'd have the axis, and we'd have like the pre-computed datas of that. Did we end up using you? I think I was rotating some stuff before. We end up using you? We used it for that. We used that for mid-angle. Maybe, you know what? Actually, I should probably just put this in here. However, that page appears to use a y inverse coordinate system, and the tangent formula is incorrect. It references which has the correct tangent formula and appears to use the same y polarity. All right, now what do we do to our circles? Or to our circular arcs? So is this related to rotation? No. It is not related to rotation. Okay, that seems to... Oh, right. Of course it's not going to line up because we're not rotated right now. But it lines up with this line, which basically tells me that this point is correct. So we expect... which one's our sidebar? Oh. Now I thought I handled this. Oh. Well, start angle, end angle. Let's start angle. Start angle. Start angle, end angle, reversed. Yeah. So we might not be handling the reversed flag. I think I've just been fixing that. No. It's going to be an arc. You've maybe only got two? Yeah. Oh, QCAD reversed. Yeah. Yeah, I don't think I'm handling that. Of course, one answer would just be to create a new one. As long as we don't save. That's must have been cast. So it probably was the direction of convenience. No, she's an arc. So let's assume that that must have been reversed. Wait, start angle. Yeah, we hit a slightly different point here for our reference. Man, that is hard to track. Oh, that was the radius of the circle. Now, we're going to start there. All right, now you, good sir, are not reversed. This is hopefully a one-time change. That didn't do it. Although maybe we had a compiler order issue. So maybe the angles are still weird? Well, if I limited it down to Aries and then did debugging on arcs, I might be able to track down that thing. But we should be converted now. That is such a weird way to error. All right, basic connectors. Oh, duos also hit arcs. Although maybe the calculations on this. No, because it's display boon connector. This is not a boundary. All right, so. And it'd be actually be kind of nice to get into the archetype from here. You have an easy way to get into that? Yeah, that would be all shapes. Okay, center from angle 5. Oh, this does cross 0, so that might be what's messing it up. Actually, both of these cross 0? That's radius. From angle to angle. 5 to 1. 1 to 4. Okay, so we have something about a slightly more than 90-degree arc that is wrapping around. I don't know if I can pipe this properly. So the midpoint I don't think is a big deal here. I don't think. Oh, we're doing... We actually do support winding. We just probably just don't decode it. So if I just decoded that reversed property, I guess I could have just done that. Oh yeah, winding. That should be fine. All right, from 5 to 1. So odd angle. So 1 minus 5 abs. Reasonable. Winding counterclockwise, so we're not doing anything to the angles per se. Why did we have that? If I had to turn on all the other arcs to figure out what broke if you took out the greater than pi. Actually, 4 does seem wrong. Yeah, that's the wider rotation. Maybe I need to be doing... Well, no, it's an opposite angle. The pi flip on that one work. So we're getting the greater circle on this. Oh, that's why we're trying to take the angle and run it through pi, because we want the lesser angle. That's slightly more than a quarter turn. But is it not correctly more than a quarter turn? Oh. Does that mean my other... Well, we do have to do from angle. So that's actually the midpoint that's overreaching. But in this case, would it be from angle... minus? Okay, that works for you. Question is, does it work for everybody else? Let's see, who has arcs? You've got a little arc. You guys have a bunch of little arcs. You've got a bunch of little arcs. Those are little arcs. We haven't done anything to this. Your ellipses. That has some little arcs. Not yet spotted anything that broke. Oh yeah, I guess these are using arc too. Mm. Does this apply to ellipses too? Not to any we're using, I guess? And where are we? I guess that's an okay point to stop. That's a whole bunch of arc stuff. Importing points is going to be a thing for highlighting areas, which would be nice. And by itself, not terribly hard. But these things can sometimes take you into surprise tangents. I might want to work on this more this week. Otherwise, it'll be Saturday morning. And the weeknights are pretty much when I feel like it. But that's it for tonight. Thanks to the support from all the subscribers and, well, people gifting subs, I guess. Good night.